Hello everybody, in this video I would like to show you a geometric definition of the hyperbolic functions, and it turns out that even in university level courses this intuition is rarely given. It's very beautiful, so I would like to show it to you. So we know that if we have a circle here with an angle, say x here, then this point is cosine of x and sine of x. This is basically the definition of the trigonometric functions due to Euler that extended it to arbitrary angles and not only to the sharp angle. And so if we were to compute the area that we have here, what is the area here? Well, the area here, we need to take the area of a unit circle is of course pi. It's pi r squared, but the radius is 1. And then we need to take x, the fraction of x of the 2 pi radians. And so we have that the area of this is half x, right? So why am I telling you this? Well, the idea is that we can define, so look at the equation of the circle. The equation of the circle is x squared plus y squared equals to 1. And basically, when we parameterize the circle in the following way, where x represents the angle, we can also say when the area is x half, when the area is x half of this sector, then the coordinates of this point is cosine of x and sine of x. Now suppose that we would like to do the same parameterization, but for the hyperbola x squared minus y squared equals 1, and hence the name hyperbolic functions, because we would like to do an analogous parameterization of the hyperbola, but we'll choose only this. So this is 1 and this is minus 1. So we'll choose only this positive part. And so what if we would say that we want to parameterize a point here, and we would call it by the name of the hyperbolic functions. So here will be the cosine, but not on the circle, but the cosine of the hyperbola. So we call it the hyperbolic cosine and the hyperbolic sine of x. And we will say, but x is not this coordinate. This coordinate is the cosine hyperbolic of x, and sine hyperbolic of x is this coordinate, right? Just in the same way as x is not this coordinate. And so if we connect this arc or this line over here, then we would demand that when, in an analogy, when the area here is half x, then the coordinates of this point on the hyperbola is cosine hyperbolic and sine hyperbolic. And actually we see, first of all, note the similarity that we have here. And it's almost as if we were to say, if we could change this, make the substitution y maps to iy, then we continuously transition from this curve to this curve, in a way. And actually it is being revealed in a course in complex analysis that in fact the cosine and the cosine hyperbolic and sine hyperbolic are basically the manifestation of the same function over the complex plane or something like this. So now let's try to derive this geometric definition of the hyperbolic cosine here. So we want that the area here would be x half. And now let's write what is the expression for the area here. So of course, by definition, this distance is the hyperbolic cosine, and this is the hyperbolic sine. And so the area of the entire triangle, if this is the origin and this is, I don't know, AB, then the area of the triangle OAB, which is right angle triangle, is cosine hyperbolic of x times the sine hyperbolic of x and half, right? But this is way too much. We need to subtract this area. So we need to subtract, and now let's use the parameterization of the hyperbola. So of course, if x squared minus y squared is 1, then y is the positive square root of x squared minus 1. But since x, the variable x, is already reserved here, then we will write it as t. So we need to integrate the function t squared minus 1, dt, and we integrate it from 1 up to the hyperbolic cosine of x. Basically, we need to have this equality, and that's the definition of the hyperbolic cosine and sine function. Now note that since this point has to be on the hyperbola, then in an analogy, since cosine and sine are on the unit circle here, then we have the trivial identity that cosine squared plus sine squared of x equals to 1, and here we have that the cosine hyperbolic squared of x minus, since it's here, minus the sine hyperbolic squared of x equals to 1. So this is the analogous identity for the hyperbolic functions. And so now let's see where does this definition leads us. So we need to compute this integral. So let us just do an intermediate computation and denote by I this integral from 1 to the hyperbolic cosine, the square root of t squared minus 1. And so let's do this by parts. So assume that we have here 1 times this, and so we'll choose this as v prime, and this will be u. And so we have uv, which is t, the square root of t squared minus 1, and we need to take it from 1 to the hyperbolic cosine. And then we basically need to subtract the integral of v, which is t, times the derivative of u. So we're going to have this is to the power of half, so we're going to have this to the power of minus half, so it's basically t squared minus 1, the square root of that, and actually twice, but then we're going to have twice t, the internal derivative, so we're going to have this expression from 1 to hyperbolic cosine of x. And let's make one more step here. So so this equals, so if we write it in the following way, so it's the cosine hyperbolic of x. This is when we substitute 1 here, it's going to be 0. So we're computing only the upper limit. And here we're going to have cosine hyperbolic minus 1. So if we remember this identity, so if we take the sign over here and minus 1, then the square root of this, since we talk only about the positive coordinates here, so in this definition, cosine hyperbolic and sine hyperbolic are positive functions, in at least in where we define in the way we define it here, and then we can extend. But so now what we're going to have is that the square root of cosine hyperbolic minus 1 is the hyperbolic sine of x. And here we're going to need to subtract this integral, which is t squared over t squared minus 1, and here from 1 to cosine hyperbolic of x, and that's going to be dt. So what am I going to, I'm going to do the following thing. So I'm going to subtract 1 here, and then I'm going to add this integral dt over the square root of t squared minus 1 from 1 to cosine hyperbolic of x. And so I changed nothing, the same expression, but now, so what we have here is that, this expression equals exactly the square root of t squared minus 1. So the integral that we have here is I again. So this integral is I, right? All of it. So, and remember we started with I equals to that. So if we now move it to the other side, what we have is that twice I equals the cosine hyperbolic of x, sine hyperbolic of x, and then plus this integral from 1 over the cosine hyperbolic of x dt divided by the square root of t squared minus 1. Okay, and if we divide by 2, then we have that I is actually half. This is something that we have already seen, cosine hyperbolic of x, sine hyperbolic of x, and plus half this integral of 1 plus cosine hyperbolic of x, and here we have dt over the square root of t squared minus 1. And so we're making some progress, but now you can say, okay, this integral for I was a hard one, and now you actually reduced to computing I to computing an integral that seems just as hard. But this is not the case, because if you've watched my previous videos, then this integral can be easily solved with the, not so easily, with the genius substitution of the, due to Euler, the Euler substitution. Today, actually, we will see that the way to solve these integrals of the form, integral of the form, say, t squared plus a squared square root of that dt, or dt square root of maybe here plus minus a and t squared plus minus a squared, is actually to substitute t as here hyperbolic cosine or sine of some u, for example, here and here. And that's the way of solving it. But we want to define the hyperbolic function, so we'll not use them. So we'll use the Euler substitution. So sorry if this was a small step aside. So now let's remember where we are. We want to compute this integral. And so let me remind the Euler substitution. So if we want to compute the indefinite integral dt of the square root of t squared minus 1, then the idea of the Euler substitution is to substitute u, yeah, you see how brilliant this substitution is, as t squared minus 1 here. And, well, why would it work? That seems bizarre, right? But let's compute what is du here. So du, so the derivative of t is 1, and then the derivative of this, it turns out we've actually computed, is t over the square root of t minus 1, and all of it dt. And so what we see here when we do the common denominator, that we see here that we have t squared plus t squared, t plus the square root of t squared over 1. So we have this. And now the genius of the Euler substitution is this is u. So what we have is that dt over this is exactly du over u. And so we get natural logarithm of u. And maybe plus a constant, but I'll write plus a constant. It's not going to matter because we're computing the definite integral over there. And so if we now substitute what u was, so we actually computed this integral. So this is the natural logarithm of this. And in fact, if we're running a bit farther, this is exactly the arc cosine hyperbolic of t, this function. But we will see why. So maybe it was too much, but let us get back to here. So that's what we had here. So let us write what is I. So now we have that I equals half cosine hyperbolic of x, sine hyperbolic of x, and then for I we would write, we need to divide this integral, so we need to add half of this integral, right? If we go back, we need half of this integral, so we need to add half natural logarithm of here we used, so it's actually gonna be this substitution, so it's gonna be t plus the square root of t squared minus 1 from 1 to cosine hyperbolic of x. So finally what we obtain here, so when we plug in 1 here, it's going to be 0. And when we plug the hyperbolic cosine, so what we see is that this I equals half cosine hyperbolic of x, sine hyperbolic of x, and plus half. And here we're going to have natural logarithm of cosine hyperbolic of x and plus the square root of the cosine hyperbolic squared of x minus 1. Okay, great. So we have computed this, but now let's remember why we needed it. So yeah, it could be a bit challenging to remember why, but remember that we defined that what we need, that x half equals this minus this integral I which we have computed. So we can write that this x half is this half cosine hyperbolic sine hyperbolic minus I. So the equation that we have is now, when we get back, is that x half equals half cosine hyperbolic of x sine hyperbolic of x and minus I. So we need to subtract this. So note that, okay, let's subtract it. So it's minus this. So it's going to be cosine hyperbolic of x and sine hyperbolic of x. Actually, I needed, oh yeah, this integral had to be subtracted, I think. Yes, I'm sorry for the mistake here. I need to subtract this integral from here because in order not to change anything. Sorry for the mistake. I had a minus here, and then this minus is a plus. So to correct it and to bring it to the expression that we had previously, I need a minus here. So that's a minus, and therefore what we have here is that the minus minus is going to give us a plus, so we need to add half natural logarithm of the cosine hyperbolic of x plus the square root of the cosine hyperbolic of x minus 1, and this equals to x half. So now what we have is that x, and this is the natural logarithm of, and say, let's call the hyperbolic cosine y, right? So write this as y, and this is the square root of y squared minus 1. So if we define y as the hyperbolic cosine of x, right, then actually we see that this function, then arc cosine hyperbolic of y, is this function that we have here. This is the natural logarithm of y plus the square root of y squared minus y, or minus 1. So this is that. And so now basically what we have is that e to the power of x is, or we can say is y minus and plus the square root of y squared minus 1. And then what we have is that e to the power of x minus y squared is going to be y squared minus 1. And then if we open the brackets here, then we're going to have e to the power of 2x minus 2e to the power of xy and plus y squared. And notice how nice that this y squared is gone from both sides. And then basically I will transfer the 1 over here. So we have e to the power of 2x and plus 1 equals twice e to the power of x times y. And finally what we get, that y, which is just the cosine hyperbolic of x, is I need to divide by 2 e to the power of x. So it's going to be e to the power of x plus e to the minus power of x over 2. Wow. So we've got from this geometric definition, we got the hyperbolic function. And similarly now we can use the identity that cosine hyperbolic squared of x minus the sine hyperbolic squared of x equals to 1 to infer that the sine hyperbolic of x has to be e to the power of x minus e to the minus to the power of minus x over 2. So that's the definition of the hyperbolic functions, and they actually parameterize the hyperbola. So if we have a point here on the hyperbola with coordinates cosine hyperbolic of x and sine hyperbolic of x, then the x is actually, and this is of course 1, so we see that the cosine hyperbolic of x has to be at least 1, and we see it over here because e to the power of x is, this is basically, this expression is always at least 2. It's easy to prove. And so the cosine hyperbolic is an even function, just like the cosine, and so we see that if this is the coordinates, then the area in here is gonna be x half. This video is getting a bit long, but I just want to give you some intuition here, because, well, it's, to those of you who would be interested, I would say a few more words about this beautiful relationship that we have. Look at the analogy, just look at the analogy that we have here. So we have the unit circle here with the equation which is x squared plus y squared equal to 1. And so, yeah, if the angle here is, let's call this angle alpha, right? Then this is cosine of alpha and sine of alpha, and the area here is half of alpha. And for the hyperbola, it's almost as if we just substitute iy, just substitute iy instead of y, and then what we have is the equation x squared minus y squared equals to 1. And then the coordinates here of a point, so if this is alpha here, in a sense, right, then it's not the angle alpha. If the area here is alpha, that's area equals to alpha here, then this is cosine hyperbolic of alpha and sine hyperbolic of alpha. This is nice. And note that if we look at the cosine hyperbolic of x, so cosine of x, let's look at the Euler formula. So it's e to the x plus e to the minus x, that's ix, and that's minus ix over 2. And the cosine hyperbolic of x is e to the power of x plus e to the minus power of x over 2. And so we see that if we were to use the extended definition of the cosine or as the series over the complex, then we see actually that what I said, that the cosine of ix is actually the cosine hyperbolic of x. And similarly, the cosine hyperbolic of ix is the cosine of x. Isn't it beautiful? Don't you find it beautiful? But actually it goes so, and the cosine is even and the cosine hyperbolic is even. And if we look at the series, so the series, Taylor series for the cosine, actually we can define it for every z here, right? Complex z. So it is the sum of minus 1 to the power of n, z to the power of 2n divided by 2n factorial, and goes from 0 to infinity. And when we look at the cosine hyperbolic of z, it's just like, removing this minus 1 to the power of n. This is just the sum of z to the power of 2n divided by 2n factorial as n runs from 0 to infinity. And this is just exactly as putting iz here instead of z, and then we transform from here to here, or here putting iz instead of z gets us here to here. So this is z maps to iz, and this is just, and here it's the same, z maps to iz, transform us, makes this transformation between them. And so you see that over the complex, the connection between the cosine, the coordinates on the circle, and on the hyperbola are actually related in this deep relation that is being revealed over the complex. And so for the cosine of z, actually we can prove that it holds for every complex z by the theorem of uniqueness. We have that this is equals to 1 for every z, and for the cosine hyperbolic squared z minus 1, and this squared minus sine hyperbolic of z squared, this is 1. And so here actually the derivative of the cosine of z is minus the sine of z, and the derivative of the sine of z is the cosine of z. But with the hyperbolic functions, they are nice to each other. The derivative of the hyperbolic cosine is the hyperbolic sine, and the derivative of the hyperbolic sine is the hyperbolic cosine. This is a nice property that they have. And what else I wanted to say here? So of course this connection is being revealed over the complex. They are the manifestation of the same function, and the Euler formula, the amazing Euler formula, gives a connection between them, and it's when the theory of complex function is studied, then those relations are becoming apparent. But one more thing that I wanted to say here with intuition from physics. So if we have these coordinates on the circle, and we have here a point which, say, I would call here, so it's going to be cosine of some alpha and sine of some alpha, right? And so this is like 1 point. And so making this transformation of rotation preserves this Euclidean distance. So if we have the distance of 2 points, if the coordinates here are x, y, right, and say that this is a point that's another point that is rotated, then what we have is, if we rotate, then the Euclidean distance is being preserved. What happens on the hyperbola is that we have, in just a remark from physics in special relativity, that this interval that we have is an invariant that's supposed to hold for every coordinate system. So we have something like this. So x squared minus c delta x squared between two events, and plus c delta t squared. This has to be invariant in all inertial coordinate systems that move with constant velocity with respect to one another. And so this has to be the same. It has to be the same in every inertial frame of reference. If we have here a frame x and say xt, right, and with coordinates xt. So of course t is not, let's call it y, and here we have the prime coordinates. This is x prime and y prime, and this moves with respect to this with some velocity v. Then we see that the relativistic transformation are preserving this distance over the hyperbola, right? So it's a hyperbolic geometry, and so the Lorentz transformation can be written in terms of the hyperbolic functions, but maybe later about this in the later video, because this one is getting very long. But I really hope that you enjoyed it, and hope to see you in the next one.